Okay, so first we have kind of a bunch of housekeeping things to talk about before we get back into clock synchronization. And I have a list here to make sure I don't forget anything. So I guess probably the first, maybe the thing that's on everyone's mind is that exam 1 is Friday. And I guess to be clear, like I call them exams because I want you to take them seriously, but it's not like a midterm, right? We haven't covered that much content, so this is really a checkup on the content that we have covered. And I will give you at the end of class, I'll do some more details on this. So I just wanted to put the reminder out there because it's probably on your mind. Okay. Then the second thing related to that, so there won't be any lecture on Friday because obviously the exam is 2 hours, so that counts for your time period on Friday. Okay. Then the third thing is I plan to use Gradescope for the exams, to handle the exams. I think many of you have used Gradescope before for some classes. If you haven't, it's very similar to Submiti, assuming you've used that before, but it just has a bunch of features, especially for online exams, that I think it's just easier for me to work with, so I would like to use this. But because it is like external software, kind of like what's the other one, Piazza, right? So it's not RPI hosted, so I guess that just makes it different, right? I mean, your data is put somewhere else. So I'd like to give you a chance to read the privacy terms. They meet all the legal requirements of like the FERPA laws and education privacy laws, but I want to give you a chance to read them. And if anyone wants to opt out, you can certainly do that. So I'm going to send an email, well, a Submiti announcement today. And that's going to give you, so that's today. That's going to give you all the information about, where to read the Gradescope terms and conditions if you are so interested, and, if you want to contact me about it. And assuming that you're on board with Gradescope, then what I'm going to do is I'm going to load everybody who's, said, is fine into Gradescope tomorrow. So you'll get a Gradescope invitation tomorrow. They'll both come via email. Okay, so that's that. And then I am going to do also tomorrow, I'm going to post like a practice exam in Gradescope, so you can, and by practice I mean it's going to have like silly questions, not practice questions, but it's mostly for you to practice using Gradescope. And so I will, announce in Submiti on tomorrow again when that's available. Okay. So you can try, see how the interface works, see how, so basically you can keep resubmitting, like you have a certain amount of, like there's a window that the exam is available, there's like a shorter window that's like your allowed time to take the exam, and you can resubmit or re-upload as many times as you want, so you can play with that interface and make sure you're fully comfortable before Friday. So that's the plan with that. Any questions about that kind of bookkeeping logistics stuff? Do you need to be registered on SIS to take the exam? Okay, you don't need to be in SIS, but you need to be in Gradescope. And so I downloaded the class list from SIS. So I guess tomorrow when I send out the email that's, hey, I'm gonna put everything in Gradescope now, like go try the practice quiz. If you don't have a Gradescope account, then you should email me and I'll set that up for you. So we don't need SIS to be involved to get any of this working, but I may not have all of the updated lists. So if you get an email saying like go in Gradescope and try out the practice exam and you can't get into Gradescope, then email me and I can add. Okay. But you're in Submiti, right? Like, because otherwise you won't get any announcement. Are you in Submiti? No. Okay, well then email me and let's get you in Submiti and then we can go from there. Okay. Great. Yes. Submittee, that's definitely, yeah. I can add you manually as long as I know that you're missing. No problem. Okay. So that's exam one, logistics. And again, like I said, I'll talk about the content at the end of the class. And then the other thing I had mentioned last week, but I will send out kind of email WebEx invitations. I'll send this weekend. And not that it's important, but the reason I'm waiting is because I can schedule like a repeated event in WebEx, like what now it's scheduled every Tuesday and Friday, but then I can go in and cancel the specific events on the dates of the exams. But I didn't want to schedule for everybody today and then immediately cancel on Friday because I thought that would be confusing. So I'll wait till after Friday and then I'll send out the invitation. And what that does for you, in case you weren't aware, is that when you go into your little WebEx menu, for those who are using the application and not the browser, you'll see a list of your like upcoming WebEx meetings and you'll show up there. And again, I will use the list that's in SIS. So if you are not there and you want a specific invitation, let me know. Okay. And then the last announcement is the project, which is due when? When's it due? The 20th, which is Sunday, yes? Yeah? Okay. I wrote that down, but just checking you guys. At 11 p.m. is what I said, in Submittee. So I see a lot of them, already turned in and turning through. So don't forget, because I won't see you on Friday in person, so I can't remind you then. So I'm just giving the reminder now. Although I probably will send out a reminder on Sunday that's like, hey, by the way, go and do this. And for those of you who are not familiar with Submittee, you'll use Git to upload your code to our Submittee server repository, but then you also need to go in the website and click submit my stuff. Otherwise, we won't have the latest version. So I'll send a reminder about that over the weekend. Okay. Any questions about the project? Sure thing. I can wait. Will the known host JSON file always be in the parent of the bin folder? That's okay. Trying to make sure I don't get this right because this has changed over the years. So the way I understand it is the way that I explained it in the source code in the project specification, is that what we're doing is we're making your bin directory on like one container and then copying the contents of your bin directory over to all of the testing containers, so each of the testing containers. And so there won't be a bin on the testing containers. You'll just have like whatever was in that directory will be in the root of your container. And the known host file will be placed also there at the root. So it's going to be kind of next to your run sh script, not in a parent directory of your run sh script. Does that answer your question, Mitchell? Yes, alongside means inside the bin folder, except there's no bin folder anymore, right? So like we're taking everything out of the bin folder and we're putting it at the root. Okay, so yes, then we're good on that one? Great, okay, all right. Next question, are we guaranteed to be able to bind to a specific port in the range? Yes, that's the purpose of the port range, is these are the ports that you are allowed to have access to. You don't need to test them. You are guaranteed to be able to bind to them. I mean, provided that your own code hasn't already bound to them, but there's nothing outside of your code that's going to be using those ports. All right. Hidden test cases. Okay, so hidden test cases, yes, they count for the grade. So the total points of the whole project is 100. So I forget how many points are visible and how many are hidden, but the remaining points are the hidden tests. So the point is you don't get to see them now, right? But you will see them when you get your grade, and you'll see whether you got those right or wrong. I know I mean, this is really common. This is how submittee works, you know, in at least as far as I understand it. So the point of these hidden test cases is really just to make sure that you don't hard code anything. Okay, so you don't want to hard code, you know, the number of sites, the names of the sites, the ports of the sites, you know, the IP addresses of the sites. Like we want you to parse that all from the known host file. There is no command that's not already tested in the public test cases, right? So they're all like, there's not like a secret thing hiding in these hidden test cases. It's really just make sure you didn't hard code anything. And so that's how it works. And so in the past, what I've done for testing is that I give you a few public test cases, and then I would do a demo where you'd come into my office and I would ask you to like follow a script, like enter this here and enter that there, and then we look at the results together. And then your grade would be on that interaction, that in-person demo. And so the hidden test cases let me just do this in an automated way. So it's not any different. Like you shouldn't know what those are in advance. You need to follow the spec and consider corner cases in your own head. And then, you know, the actual evaluation is going to be, you know, checking one, does your code do what the spec is, but also two, did you consider all the proper corner cases? It's not up to me to tell you what the corner cases are. So that's the purpose of the hidden test cases. But of course, there's not going to be a secret grade, right? Like I'm not going to be like, you got a 72 and not tell you why, right? Like once you get your grade, you'll know what happened and why. So, does that answer the questions about the test cases? Okay, then I think this is related, is do we see them in rainbow grades? So I'm not going to use rainbow grades for this course. Not going to use rainbow grades. So the way that you'll see this is just going to be like when we return your assignment to you in Submiti, you'll be able to see the graded assignment. And I'm not 100% how to do this in Submiti, but I will either just make them not hidden at that time, so you can then just see the execution of the cases. I think that's probably what I'll do, so that you can see everything. So you'll be able to just to see your scores in Submiti after. I'm going to go through and review them and make sure that there's not like any unexpected, I don't know, like character mismatches or something, you know, something that's not, you know, anticipated Submiti behavior. And then I'll just release everything after the due date so you can just see what happened. Are there so many corner cases, really? I mean, it's fine if you're not sure like what are good, you know, well, race conditions are bugs, not corner cases. So I don't want to use rainbow grades because your grades are going to be in Gradescope, so it doesn't help with any of that. So you'll be able to see all of your grades in Gradescopes except for the project. So you'll have that. But yes, don't have any race conditions. That's my recommendation. Okay. Any other questions? All right, so I see people have been posting questions also on the forum in Submiti, and so I'm certainly happy to answer them there. Just please don't post code, that's what we ask. All right, I guess we will get back to clocks now. So last time we had talked about kind of the timing of how often you need, well, why you would need to synchronize clocks, right? Because the clocks drift, and then assuming you wanted to have even these physical clocks be within some accuracy of one another, how often do you need to synchronize? And then I kind of introduced, well, okay, if we're going to synchronize, how do we do it? And the idea is that we have some server S, which is a source of UTC time. That's our absolute time. And we want to sync a single process's clock to this UTC time. And we're going to talk about two different algorithms to do this. And the algorithms work in different system models. So if you remember back to the introduction to this class, I told you that when we learn about an algorithm, we always learn about it in the context of some assumptions about how our system behaves, and we analyze it that way. And so the first algorithm that we're going to study is going to be an algorithm for a synchronous, this is always hard to say, synchronous system. And does anyone remember what a synchronous synchronous system is? So we made some assumptions about kind of the message latency and the computation latency. Yes, not synchronous. That's, yeah. Yeah, so the one I'm looking for here from someone who I hope knows, the known upper bound, right? So the key here is that we have some bound, we're going to call this bound max, and max is a known upper bound on, we're going to say this is the one-way message delay. And so that's the amount of time it takes the message, the maximum amount of time it can take a message to go from a sender to a receiver. And we're going to assume that this is a bidirectional thing. So, we're going to be sending messages between S and some process PI, and max applies in both directions. So the maximum amount of time it could take PI to send a message to S, and the maximum amount of time it could take S to send a message to PI. And we're also going to assume that we know min, which is a known lower bound on message delay. And so we can always assume we have a known lower bound on message delay. Messaging is never instantaneous because we are, by definition, in a system where the processes are spatially distributed, and therefore we have to just deal with the speed of light, right? So assuming that we're not doing some quantum computing kind of scheme, the way that information is going to get transmitted from any process to another is by sending messages that at the very, could go no faster than the speed of light. At least we'll just kind of rely on that realistic assumption, okay? And for simplicity, I'm going to assume that computation is instantaneous. And this is going to seem maybe unrealistic, but you can kind of like fold the computation time into the message latency, so that message latency could be like the time it takes the message to be, sent, delivered, and processed. So we can kind of absorb the computation time into our message latency. We don't have to write it explicitly, and sometimes that's a little easier. So by just saying we assume it's instantaneous, meaning we assume it's already accounted for in max and min. Okay. So for this synchronous system, the kind of algorithm we're going to use is a push protocol. And for the purposes of this course, protocol means the same thing as algorithm. It's just sometimes people use the word protocol. It doesn't always refer to an algorithm in other places, but in this class, it's going to refer to an algorithm. So the way this algorithm works is we have our time server S, we have our process PI. And so remember I said it's push, which just means that periodically at the length of time, determined kind of via the earlier exercise that we did on this, the time server is going to send a message to PI, and it's going to attach to that message the time, where T is sort of the time the message was sent. So S looks at its clock, it says what time it is, it sticks that time on the message, he sends this to PI. And then now the question is, PI is going to receive this message. What should it set its clock to? And we're going to make some assumption that PI wants its clock to be as accurate as possible. So the way that we figure out, right, so we can't just set it to T, because why not? I mean, I guess it could, but why would that not be a good thing? Right. So there's message delay. So we know, and I see already in this, in the answer says, we know that when PI receives this message, that at least min time has passed, right? It took at least min time for that message to go from S to PI, right? So yeah, so we know kind of, and I'll write this down the way that I think about it, but we can think of, well, what are the possible range of times? This is just, I'm just drawing an interval. When PI receives this message, what are the possible times that it could be, at PI, right, when it gets the message? And so we know it has to be like the lower bound of this interval has to be t plus min, right, because it took at least min time for that message to get there. And then the maximum amount at the top of this interval can be what? We'll see if they're already, but just to be clear, in the worst case, t plus max, it took max time for that message to get there, right? So yeah. So we know that when PI gets this message, that the time is somewhere in that interval. And if it wants to kind of minimize its error, what should it do? Yep. Pick the middle, take the average, exactly, right? That's exactly what you want to do. Now, this is because we assume we don't know anything else about the messaging other than we know max and min. So like we don't have a probability distribution, we can't do anything fancy. All we know is max and min. And if we want to minimize the error, we're going to set time to this. So then the question becomes, well, what is this? And so I do this very pedantically because I tend to make silly math errors. So I'll write it out all for you, but obviously most of you probably already know the answer in your head. But first we're going to figure out what's the width of this interval, right? So that's t plus max minus t plus min, which is just max minus min. And then what do we want to set the clock to? So we're going to start with the lower end of the interval, t plus min. And then we're going to add half the interval with max minus min over 2. And we end up with, write this on another line, t plus max plus min over 2. Okay? And so then the next question that one would ask about this is, so how accurate is PI's clock after doing this? And that is just kind of this half the interval here, right? Like how far away can it be from any true time? And it's going to be max minus min over 2. So we'll write it's equal to plus minus max minus min over 2. Is there any questions about that? All right, so that's pretty straightforward, hopefully. Oh, sorry. Why is it max plus min and not max minus min? Yes, see, this is why I write everything out, because I am terrible at kind of this basic and make these silly mistakes. But if I look at what I have here, I have t plus min plus that half an interval width. And if I just do the math, then it works out. See, because we have a min, and then this is like 2 min over 2 minus min over 2. And we end up with min over 2. So that's why it's plus. Yeah, this is why I write it out, because it's not that you don't know how to do this. It's just that I make silly mistakes. So write the whole thing out, and then you hopefully won't run into that trouble. All right. Any other questions? Would you want a condition on PI's previous time where the error between this and t plus max. So this is a good question. And so these are not kind of, we're not making any assumptions on probabilistic distributions of message delay. So this is not going to be a stochastic approach to this problem. And there are, I mean, if we look at kind of NTP, so real world time server algorithms, they're going to do something like that. They're either going to take multiple readings and use kind of an estimation-based approach, but those are still kind of relying on some assumptions about the probability distribution, that it behaves in a certain way. And so if those assumptions fail to hold, then this is kind of what you're stuck with, right? So that's why I would say that it's not doing anything clever in terms of probabilistic distribution, but this is the real world, so we can't really rely on these probabilistic distributions to be true anyway. So I guess I don't know if that answered your question, but yes, you could do this, but this is not the method. This is a little more basic. Okay. I mean, that's always the problem with probability in the real world, right? Okay, great. So that's kind of algorithm one, not so bad. And now we're going to look at a different system model, which is the asynchronous system model. And as I mentioned before, we can still have min in an asynchronous model, like this, the speed of light still exists. So we're going to still say that we have a known lower bound on message delay. Okay. But in this case, because this is an asynchronous system, we don't know the max, right? There is no known max. So there's no known upper bound. Okay, so I see in the chat about the offset as the average of the expected min and max delay. I mean, if you want to give it a probabilistic interpretation, like that's up to you, but it's not a probabilistic algorithm. So I don't know if I would, I'm not sure if I would think of it that way. But yes, one could interpret it different ways, sure. Okay, so we have no known upper bound on message delay. And again, we're going to assume computation is instantaneous, kind of the same simplifying assumption as before. Okay. And this algorithm now, it's called Christian's method. Not sure why it's a method and not an algorithm, but that's what it's called. And this is, if you remember what I talked about last time, but it's going to be a pull protocol. And what that means is that we have the server S and still PI, and instead of S proactively telling PI the time, PI is going to send a request for the time to the server, and then the server, upon receiving that request, is going to look at its clock, see what the time is, and it's going to send back the time, right? And so again, now the question is, what does PI set its time to, what set its clock to when it gets this message from the server? And in addition now to just having the value on this message, we're going to have a little bit more information. And PI, what it's going to do is it's going to start a timer when it sends that message, and it's going to stop the timer when it receives the response to its request. So it's recording the round trip time. So it's recording the round trip time, which I'm going to call T subscript RT, from the send of its request to the receive of the response, the message from the server. So this is the information that it has. And now, same question is, what should PI set its clock to when it gets this response? And so I'm going to follow the same method as I did for the previous algorithm. I'm going to make my interval. So when PI gets the response, what's the kind of the earliest time it could be at the server? Okay. I see several answers. Okay, I see t plus 2 min. Trevor, do you want to hop on the microphone and explain why you think that? Or if not, Trevor, then just say no. Or 2 minutes. Hopefully it's not 2 minutes. But someone want to, Trevor, did you want to answer? You can say no if you don't have access. Okay, there's 2 messages. You have to add 2. Okay, so let's be clear. What's going to happen is that we have T here, right? Gets recorded here, and then it just travels across to PI. So the intuition is that there are two messages, but they don't both get factored into, you know, kind of this part. The lower bound is really just referring to the one way. So what's the lower bound? Is it? I'm not sure. T subscript min. I'm not sure what that is. I see T plus min, right? So I see a few T plus min. So this is what I'm looking for. Maybe that's what T subscript min, but it's T plus min, right? Because there's a message, it starts at S, it floats across the ether, it gets to PI. The fastest it can possibly get there is min time, right? Nothing's changed from the previous case. And so the lower bound of this is T plus min. So far, so good. All right, so what's the upper bound of this interval? What's the latest possible time it can be at the server? Ah, thank you. What's the latest possible time it can be at the server when that message gets there? Okay, so T plus max, we don't have max anymore, right? We don't get that anymore. Infinity. Well, probably not infinity, because we do have some other piece of information, right? We have a round trip time. Yeah, so I see a bunch of you are throwing that out there, that somehow we can use this round trip time. And I see the right answer there. So we know that it took a certain amount of time for the request to go to the S and then the response state back to P, right? And so what if we said it was T plus TRT? What if we said that that was the upper bound? What would that mean? That would mean that all of the message latency happened on the response message. And the first message could have been instant, which, is that allowed? No, right? So how do we accommodate for the first message? Right, so subtract min, right? So we want to subtract min. So that means that it took min time for the message to get from PI to S, and then it took the whole rest of the time for the message to get from S to PI. And so that's the upper bound of our interval. Make sense? Okay, so questions, why are we subtracting min? So the idea is that we have a measurement of from S to PI. I'm sorry, from PI to S and then S back to PI, right? And this whole measurement is TRT. We don't know, we don't have any information how that round trip time is distributed. Like, we don't know that it took equal times in both directions. We have no idea, right? All we know is that each of these arrows took at least min. That's all we know. Well, so that's all we know. And so we can say that this top arrow took at least min, and then possibly the rest of the time was on the bottom arrow. And that's like our worst case for the upper bound of the interval. Min is no longer needed since we have TRT. Well, we account for min in the upper bound, right? So this could take min, and then this could take TRT minus min. That's kind of our worst case on those two arrows. Yeah. Make sense? But what was in there is we still haven't decided like what to set our clock to, right? So kind of maybe your intuition about what to set the clock to is perfectly right, but trying to explain why it's a good intuition. Okay, great. So that's our interval. So again, we want to find the middle. And so I'm going to do this in the silly way because I'm prone to making mistakes. I don't know if that's true or not. I just say it. So we're going to just do the upper end minus the lower end. Right, so okay, so let me just, I'll answer your question, Matthew, and just, okay, I see lots of stuff going on here. Okay, let's just check my math and then I'll go back to there. So assuming you buy my interval bounds, then I'm going to subtract the upper bound from the lower bound. I'm going to end up with TRT minus 2 min. Okay. Now let me finish what we're going to set the clock to, and then let's go back and rethink why I'm setting those bounds what they are. Okay, I see all your questions. I promise I will come back to them. Okay, so if that's our interval width, then we need to figure out what half the interval is, right? And that's going to be TRT over 2 minus min. And then PI is going to set the clock to the lower bound of that interval plus the width of half the interval. Which is going to be t plus the round trip time divided by 2. Okay? All right, so let's kind of go back again. Now, so I think that maybe when some people were throwing the dots, like, but why don't I just set it to t plus t over 2, right? So maybe that, like, you just jumped right there and you're like, let's divide the round trip time by 2 and then add that on. And yes, that's exactly what you're doing, but this is why, right? This is why we're doing it. So, yes. So let's see, let me go back. So why is this an upper bound instead of an, okay, I think you got it. Does anyone still have questions? Okay. Okay, I think we're good. All right, so now we know what we set our clock to. And now we have clock accuracy, which is just going to be the length of half the interval. So it's going to be plus or minus TRT over 2 minus min. So that's telling me that if I use this algorithm, then I can guarantee this is how accurate the clock is, you know, within this error bounds after I'm done. But of course, with this one, we're making a little bit of assumption, kind of based on the last class, that this is going to assume that the clock drift at PI is negligible compared to the time this whole process takes. can't spell negligible. So last time we talked about how clocks, even correct clocks, had a drift, right? So that they weren't keeping perfect time. And yet here we're relying on round trip time. And so if the clock drift is really, really, really bad, then that round trip time is going to be kind of nonsensical. So that's why we have to sort of make this assumption that that clock drift has to be very, very small compared to the round trip time. So we're asking about the why. Celia, is that not what I wrote? Oh, you want this? Is that where the confusion was? Yes, that's what it is. Yes. Sorry, sloppy parenthesis usage. Yes. Okay. All right. Any other questions about this algorithm or clock synchronization? Okay, so that's that topic. And so now I want to move on to the next thing, but I'm just going to do a quick stop of the recording and restart because it's easier if the files are not quite so huge.